is Sabine Andrei Tsena. He will talk about the algorithm of preferences. The title could stop here, but on it goes. It says visual evoke potentials for architectural latent space curation. It's on.
Thank you. You can hear me. Okay, thank you. So hi, I'm Sabine. I'm here representing a team of architects and PhD candidates from the Ioan Mincu University in Bucharest, Romania. Also a team of neuroscientists from the Genetic Center in Bucharest, Romania, and a team of computer scientists from the University of Bucharest. And some of you might have this question in mind. Yes, I flew here all the way from Bucharest 2 days ago, and yes, a bit of jet lag, but let's go on. Our research study and project, the algorithm of preferences, mostly deals with trying to include emotions, feelings, and preferences into the generative design process. So we are in the early design concept stage, and what we essentially did was use a EEG-based ERP on a P300 component, BCI, for the curation of a large space generated by a generative design algorithm. So why generative design? Well, it has been in the talks for the last like 20 plus years. And while design, in essence, I feel like is a matter of asking good questions, and classical design is about having a real solid answer to it, generative design is mostly continuing those questions, more like asking an open question and seeing all these different possibilities that you might get. And this has very high potential because from some part, it's a very high creative help because you might find solutions that you or your team might not have ever thought about. So that's very valuable and precious. But on the flip side of this, the problem with having lots and lots of options is that if an architect or a team of architects wants to go through them, it's going to take a lot of time because you need to actually access your brain power and sift through all of them. And it's not only a problem of time, but it's also a problem of choice. And as research previously showed us, having few choices might be a bad thing, but also having lots of choices might lead to decisional paralysis and actually hinder your design process. So the main focus of our study is seeing how we can further narrow down, not only by simulations and optimizations, but also by using emotions and preferences in the so-called algorithm of preferences that essentially wants to balance the computational power of algorithms with the more sensitive and nuanced decision-making capabilities that us humans and architects have. So usually when we are making decisions, we as architects try to feel like we are very rational, like we need to balance economical costs, sustainability, the stakeholders' needs, our end clients' needs, and this all feels like very logical, very stoic thinking. But actually, research shows us that even if in these very rational decision-making processes, there is a very large net of emotions that are at play. And we wanted to tap into that, more specifically in the 95% of the fuel of decision-making processes, which are automatic and unconsciously driven and focused on emotion and personality. And a way to do that, to actually figure emotions out, is by using effective computing strategies and sensors and both physiological and behavioral tools. And we in our specific experiment have been using EEG. Our experiment had 3 stages. More specifically, the first stage was the generative design part, which I talked about before, was about making and generating this large search space, then sifting through it with classical simulation and optimization kinds of curation, of algorithmic curation processes, and then taking these results as very simple images, very basic images, showing them to a subset of 30 practicing architects and asking them just behaviorally, not with the EEG yet, just by looking at those images and asking them to explain how they made them feel This was the second stage, and that from that part we got the emotional results that these images were imprinting on the people. We selected the best and least performing and some medians out of them, and then we showed them to in the EEG setup to see if we can actually, using monitoring the brain's activity, see if there is a direct correlation between the emotion that people usually declare on these kinds of surveys and their brain activity. So that was like the main point of the experiment. So as I said, the first point was generating a large search space. We chose like very abstract urban tower shapes because we didn't want to actually have materiality or other things that would very highly influence this EEG process. So we chose only abstract shapes and few color, just the tower in the middle had color to had a point of fixation because they were very few seconds shown to the participants, and that was needed to have the clear point of fixation. So this was a large space. We wanted it to be unbiased, so it was kind of a 14,000 trillion design possible options. We made it specifically this large so that no one person could actually go through them one by one. We then used the classical genetic solving model to grab and optimize some of these solutions and to get to a Pareto fund that is like a how to say, a compromise between different optimization parameters that you use, but still generating a quite large search space, at least of 300 solutions. We took all these parameters that were grabbed from the space to actually have them and feed them back after we have the emotions and the emotional results into the algorithm. And the second stage, as I told you before, was about having a behavioral study and using these self-assessment mannequin assessment scales that are quite useful for visual identification of your emotions because you don't really think that much about them. There are valence, arousal, and dominance. Valence being from negative to positive of the emotion. Arousal being the intensity, and dominance being the level of the control you're feeling on the emotion that was felt during what you see. And we both chose to present the shapes both in and without context to see if that made any changes to the response that people had to seeing the shapes. After we got the results, we saw that there was quite some variance in the individual level in the arousal, valence, and dominance scale. But on the statistical level, there were some clear tops, bottoms, and medians for these solutions, and some specific images that people looked at and statistically rated higher or lower on these three scales. And we chose only those specific images to be shown on the EEG because we wanted to make sure that they are quite differentiated on a statistic level because we work on a statistic level. So this was our EEG experiment setup. We used a dry electrode EEG system from wearable sensing with 24 channels. And we presented, it was not very immersive, it was just an image because we did not want to affect very much on the EEG system because we used EEG-based event-related potentials and more specifically the P300 component in the oddball paradigm. And if you know about this, these are those experiments that use quite like boring and unexpected signals to see if the brain gets a reaction. So that was the purpose of our study, to see if from a range of solutions, one or more of them would actually give this strong reactions to what you were seeing. So that's why we chose more specifically the P300, the visual evoked potential component. So we gathered data and we chose the late potential 1 second time for the experiment. More specifically, we chose from what I told you about before, from the valence, arousal, and dominance scale. From the data that I'm going to present here today is just the valence part of it, because that's where we got the more, that's where we are right now with the analysis of the data. And as you can see in the images, as you might know, the brain activity when you are experiencing visual stimuli goes from the back of the head, from the occipital to the central and the frontal parts of the brain. And at different points, we can choose and differentiate between the reaction that people had when they were looking at these images. So we compared only the valence, maximum, minimum, and medians images for these studies. And we have the main purpose of it was differentiating between them, seeing if the brain actually has a different reaction between positive valence, negative valence, and an average valence, something that wasn't very, didn't give much of an impression or a reaction to it. So we had gathered the statistical relevance in comparing positive and negative valence. So right now we can statistically say that there is a difference in the behavior of the ERPs when you are comparing something that you find positive or with something that you find negative. So in an actual workflow kind of situation, using the headset, the BCI could say, after showing the image for like a third of a second, the BCI could just react and say, okay, the participant liked this image, or the participant didn't like this image, or whatever image or kind of media that you would want to use for the workflow. So that would mean that in curation type of way, you could very fast identify which images or the different design solutions gather a positive impact or a negative impact, to use it to further narrow down the curation. And we also got a statistical relevance comparing positive valence and median valence, rather than like the ones that got a positive response and the ones that got a median and average response, that were not good and not bad, just medium. So we can now, from our current workflow and the current experiment, we can differentiate in the power experiment between positive and negative reactions, emotional reactions to an image, and from positive and average reactions to an image in different channels and at different intervals on this 1 second interval. And our next steps will be to actually finish analyzing all the data that we've gathered from the third stage of the study, and to also compare the arousal and the dominance scale in the images to see if there are statistical relevances there too, and we can identify how a person feels about those parts of things. And then using the preferences that the people, either statistically as a group or individually, declared for, not declared, identified by the EEG, we can then reuse those parameters that were initially fed into the algorithm, compare them with the results from the EEG, and refeed them into the algorithm to actually get to the perfect solution, either for a person or a group. And then we would want to extend the study and change the types of shapes, maybe introduce more texture, more color, more variance, different types of contexts, to see if these results actually hold up and are not only limited to this context. So that would have been the initiation for this relational intelligence model that uses generative design and algorithm parameters, and then gets an emotional reaction, and then refeeds it in a feedback loop to the beginning, and narrows down this large 14,000 trillion space to maybe one perfect solution. So that is one way to tackle this paradox of choice that generative design brings us. And we are happy to have presented it here in front of you. And I think my time is up, so I'm open for your questions. Thank you very much.
Thank you, Sabine.
Thank you.
We have time for one question. Let me ask a question. You're talking about the Pareto front.
Yes.
Do you have to assume additivity of features to construct?
Can you
Additivity in the sense that they add up to increase the quality of experience. Adapt in the sense of increasing it always and not subtracting, for example, or multiplying.
Can you rephrase the question? I don't really think I understood it.
Well, the concept of Pareto optimality and Pareto
Yes.
front, they come from economics.
Yes.
And there you have to always make an assumption of whether effects of features, they add up.
Right.
Sort of equation that describes how they work
Right.
together
Mhm.
in that sense.
Well, that could be positive or negative. It was one way to sift through these initial design options. This is not the only method for algorithmically narrowing down the search space, but it's one option. So we chose that one because it was more accessible to us in the first place.
I understand. Thank you so much, Sabine.
Thank you very much.